Hello, my name is Felix Steinfurt, and today I'm going to talk about the topic of my master thesis, Reusability in Systems Engineering, translating SysML to SysML v2. First of all, the motivation behind this thesis. The systems modeling language is a graphical modeling language, which is used to model systems in model-based systems engineering. It enjoys widespread use in multiple systems engineering domains. Its successor, the SysML v2, is currently in development, and in contrast to its predecessor, it is predominantly textual and based on a new technological space. The widespread use of its predecessor causes a demand for the reuse of existing models, which in turn fuels the need for conversion of models from SysML to SysML v2. In order to fulfill that demand, we present a conceptual translation of SysML to textual SysML v2 and hereby enable model migration and facilitate a faster industrial adoption of the new standard. The systems modeling language is based on the UML. It follows a definition-focused modeling approach, which means that any element usages are previously defined and typed by their element definitions. The systems modeling language consists of 9 different diagram types, which can be seen on the right-hand side, which are used to model the structure, behavior, parametrics, and requirements of a system. There are certain problems that the SysML inherits from the UML, which on the one hand is the redundancy of elements. For example, classifiers, classes, and types are pretty redundant in their functionality. This redundancy forces engineers to know all the different redundant elements, which adds unnecessary complexity to the language. Furthermore, SysML lacks the precision needed for reliable analysis and execution. The SysML v2 aims to solve those problems. It is based on the kernel modeling language, which is designed to bundle similar UML and SysML elements to singular elements in order to reduce the redundancy and complexity of the language. SysML v2 has no strict separation of structure and behavior and allows to combine different structural and behavioral elements in single diagrams. It also allows for more formalized requirements by being able to provide constraints in requirements, which enables automated requirement verification. In this context, verification means the evaluation whether a system complies with the requirement. The SysML v2 follows a usage-focused modeling approach, which means that usages can be modeled in a more natural manner and are able to be untyped so that there is no need to have a definition for a usage previously defined. This makes it especially easier for non-specialists to model with SysML v2. The definition-focused modeling approach that is predominant in original SysML modeling is still supported in SysML v2, which is especially good for our mapping, as we can just map definition-focused models to definition-focused models. The SysML v2 also provides a specification of analysis and calculations and aims to include an execution semantics, which as of now is still work in progress. Our general transformation approach of SysML to SysML v2 is to convert graphical SysML elements to textual SysML v2. This approach provides some advantages over mapping towards SysML v2 meta classes, which for once is the independence from specific modeling tools, as all modeling tools will be able to interpret textual SysML v2 once it finds its way to be supported by those modeling tools. And in our comparison of different versions of the SysML v2 specification, we saw that SysML v2 textual syntax changed less than the underlying meta class structure, and therefore in this current development phase, we followed that textual SysML v2 is more robust than its underlying meta class specification. The goal of our thesis is to provide an as complete as possible mapping, and we do so by making an element by element transformation ordered by the SysML diagram affiliation. In this case, the element information from different diagrams of the SysML model is bundled in a singular SysML v2 element. And in case that no simple equivalent element is found, we discuss alternative, more complex mappings. Furthermore, we provide a documentation of interesting differences between SysML and SysML v2. Our mapping can be exemplarily shown with the constraint block element in SysML. A constraint block in SysML contains constraint parameters, constraint properties, and constraint expressions. The equivalent element to a constraint block in SysML v2 is a constraint definition, which can be seen here in the mapping of constraint block 1 to constraint definition constraint block 1. Parameters of the constraint block are translated to attribute usages of the constraint definition, which is seen here, where the parameters x and y are translated to attributes x and y. The difference between constraint definitions in SysML v2 and constraint blocks in SysML is that the constraint definition in SysML v2 allows for only a singular constraint expression. Therefore, in order to provide logical sound mapping, we map constraint properties to reference usages of the constraint usage. And this can be seen here, where the constraint property nested is mapped to the reference usage nested of constraint block 2. In this diagram, constraint block 2 is not further defined, so we cannot be sure what exactly is contained in constraint block 2. When we mapped all constraint properties to reference usages, we then use a conjunction of all reference constraint usages and constraint expressions by using the conjunction operator AND in order to provide a singular constraint expression that fulfills all the constraints which are defined by the different constraint expressions and the constraint properties of the constraint block in SysML. In our example, this is shown by the constraint expression x and y and the constraint property nested, which are conjuncted into a constraint expression x over y and nested. A second example of our mapping is shown by the mapping of control flows in activity diagrams. Here, actions have the equivalent SysML v2 element action usage with the keyword action. Here, action 1 and action 2 are mapped to the action usages action 1 and action 2. And the UML specification defines control flows as edges that start an action node after finishing the previous one. Therefore, we looked for a similar element in the SysML v2 specification, and we found that successions on action usages in SysML v2 are a special kind of connector that asserts that the first action must complete before the second begins. And therefore, we translated control flows to successions from action 1 to action 2. The SysML v2 provides its own transformation approach in its specification. This approach is still work in progress and mostly maps UML for SysML elements. Although with the recent February release, this is not entirely true anymore, as many new mappings are now included. This approach provides a mapping from UML and SysML metaclasses to CurML SysML v2 metaclasses and includes a computational mapping of property values by the use of OCL conditions. This use of OCL conditions for the computational mapping can be seen here in the underlying table, where the client property of a SysML v2 dependency is mapped from the source element of the original SysML dependency. There are some mapping complications, which can be exemplarily shown with the different mappings of control flows between our transformation and the SysML v2 specifications transformation. The SysML v2 transforms control flows to associations, which is a more general mapping than our mapping to successions, as associations do not require completion of the previous node to be taken. And therefore, our mapping is more in line with the UML specification's definition of control flows. The complication of the mapping, though, is that the SysML itself provides no fixed semantics, and the SysML v2 execution semantics is still work in progress. Therefore, we cannot be entirely sure which semantics a systems engineer who models a system thought of when modeling the system. And there's only one possible solution to this problem, which is to provide multiple mappings based on the underlying semantics of the SysML model that the engineer who modeled the system thought of during the modeling process. But this would require an analysis of all the different semantics which are used in the context of SysML modeling. We also developed a prototype in form of a plugin for MagicDraw to convert graphical SysML models to textual SysML v2. Our plugin works in the following way. First, we load the model into MagicDraw, and then we take the model's containment tree and put it in our wrapper class that wraps the MagicDraw elements of the containment tree to wrapped elements. Those element wrappings are done in order to provide an easier handling of the elements and being able to define additional methods on those elements. We decide to split our output of the plugin in multiple files for a better overview when mapping large systems. Therefore, we handle packages of the model as folders, and as the SysML is a definition-focused modeling approach, we handle the elements that we map to definitions as those elements that we write to separate files. Therefore, we take the generated model tree and generate compound class instances for those elements that are mapped to definitions. Those compounds are then forwarded to the printer classes that print the compounds to textual SysML v2 and therefore provide the SysML v2 model structure of packages and those definition files. We evaluated our approach on the active phasing experiment, which was developed during the development of a European extremely large telescope project, which is planned by the European Southern Observatory. And the APE is developed as a breadboard for the evaluation of different types of wavefront sensors for telescopes and the integration of a segmented aperture control into an already active telescope system. The goal of the active phasing experiment is to provide an accurate alignment of the telescope's segmented mirror, which can be shown on the right-hand side here. This is the segmented mirror, and the goal is to provide a nanometer accurate alignment of those different mirror segments. The SysML model of the active phasing experiment is developed by the Gesellschaft für Systems Engineering, and it was developed as a case study for using SysML for solutions to challenging model-based systems engineering problems. We will now show a short demonstration of our plugin in MagicDraw on the APE reference model. In order to load our plugin into MagicDraw, we just have to put it in the plugins folder, and when then launching MagicDraw, it will automatically launch with it. Here we can see an activity diagram that describes the behavior for detecting segment and shape errors for the different wavefront sensors that are evaluated in the APE. We can also see its position in the containment tree, where it's included inside the folder structure. In order to export this APE model into SysML v2, we press on the Export to SysML v2 button in the diagrams toolbar and choose the file location, and then it converts the model to SysML v2. Here we can see the example of the set activity diagram for detecting segment and shape errors and its mapping in SysML v2. First of all, we see that we generated imports for the activities that type the call behavior actions of the model, as those activities are in other folders and therefore not just accessible to the action definition that maps the activity diagram. The parameters of the activity are mapped into incoming and outgoing items of the action definition, and the call behavior actions are mapped to actions. Hereby, the actions are no longer unnamed in order to properly being able to define the object flows. We needed to name them. Therefore, we used the lowercase version of the activities name. The incoming and outgoing object flows of those actions are mapped to incoming and outgoing items of the actions. And in case that an object is a flow, the incoming item is defined as a flow from the previous item. for example, for the Shack-Hartman sensing, flow from WFOS to WFI. Or in case that it is defined as a stream, for example, for the flow from the split field for phasing sensor to diffraction sensing. The incoming item WFI is defined as a stream from split field for phasing sensor WFO_D. Last but not least, the item flows from incoming parameters of the action definition and to outgoing parameters of the action definition are bound to the call behavior actions that those parameters flow from or flow into. This is seen, for example, for the incoming item WFI on the split field for phasing sensor, which is directly incoming from the parameter WFI, which by use of an equal sign is bound to the detect segment and shape errors.wfi parameter. The same is true for the outgoing parameters. In summary, we provided an as complete as possible mapping from SysML to SysML v2. We discussed around 140 elements and did not include sequence diagrams and use case diagrams yet, because they are still work in progress in the specification. And we documented a lot of interesting differences and provided suggestions for model modifications to take advantage of new features. We also developed a prototype as proof of concept for our mapping and evaluated that prototype on the APE model by the GFSE. And therefore, our transformation enables the migration of existing SysML models to SysML v2 and facilitates faster industrial adoption of the new standard. Thanks a lot for listening. This was the topic of my thesis.